And hello, everybody. We are going to just give a really quick review on some optics because as we've started with low vision to the definition of low vision, the different diseases that can affect somebody's vision, whether it's visual acuity, whether it's contrast sensitivity, whether it's the visual field, we have to get into some of the optics of how a lot of low vision aids work. We break low vision aids down into those that have optical mechanisms like lenses and magnifiers and telescopes to non-optical. Well, for the optical, we have to do a little bit of review. So instead of just assuming that you remember everything, we're going to do a really quick review. And if you remember all this, great. If not, it's a nice refresher, and that'll be part of this week's. So what we'll do is, since we're sharing this, let's share this. And we'll put this up and let's give you the right setting. And so let's go with the very basics. We are used to the plus lenses versus the minus lenses. And again, if we have a plus lens, it is convex in terms of its shape, and it will converge light. It will have a real focal point. This is sort of if we have a plus lens and parallel light comes through it, and then it converges, it'll converge to a specific point. I use the analogy often where if we're out in the sun, it's been very sunny, 90, 100 degrees recently. If we have a magnifying lens, we can hold it up or down, and at some point, it'll all converge into one small point. All that light comes to a point focus, and it gets very hot. It collects all that energy and puts it in one point. And that's a plus convex magnifying lens. It has a real focal point. When I look at it, if I take and look through an object and I look at, say, an exit sign, if I move the lens to the right, the exit sign will go to the left. It has against motion. That's what we used to use back in the day before lensometers. We would actually try to determine how strong a lens was by taking an existing pair of lenses. We're trying to figure out what the power was. We'd look at an object or a line, we'd go back and forth, and we'd offset it with a series of plus or minus lenses, and we could neutralize that power and then determine what the actual power in the pair of glasses was without using a lensometer. And that's because we could use a plus lens moving it back and forth will have what's called against motion. If I move it to the right, the object I'm looking at looks as if it's going to the left, and vice versa. It does, in fact, magnify. I can adjust how much it magnifies. Lenses can magnify, but there's both a power portion, like a plus lens magnifies, minus lens minifies, but you can also manipulate that with how the lens is shaped, what the base curve is, how thick it is. But by and large, for our simplistic purposes, a plus lens will just say will magnify for now. And it creates a pin cushion distortion, and this is more of an optics type thing. So let me show you what that looks like real quick. That's sort of important. I like this one right here. So pincushion effect is, and this sort of makes sense because the farther away it is, the more it actually magnifies. So pincushion plus lenses have this pincushion distortion, and the corners for a square object look like they're farther out than the sides. And so those are my plus lenses. And they're obviously absolutely basic. Plus lenses are thicker in the middle and they're thinner on the edge. So conversely, minus lenses, they diverge light. When light comes in, they will actually spread out and go away from each other. There's no point far away where they'll ever meet up again if you don't manipulate them any other way. It does not have a real focal point. It has an imaginary focal point, which we'll go into a picture in just a moment. These have with motion, they minify, and these have barrel distortion. Instead, it looks like this here. That barrel distortion is right there. So minus lens looks more like that. So those are our, if you had an ABO question, if you wanted the real basics, how lenses work, that's great. Well, we're going to be using a whole host of plus lenses for low vision, because we're going to do a lot of magnifying. We're going to do a lot of using plus magnifiers. The problem is oftentimes we need to make so much magnification and so much plus that we have to make the lenses very, very strong. And when we make them very, very strong, we generally have to hold reading material at the focal point. The focal point or the focal plane is very important because if I have a really strong lens, the focal point is going to get closer. We have to be able to compute where light comes to a focus there. So converging lenses, obviously, I can have biconvex, I can have plano-convex, or I can have a meniscus where one is convex, one is concave, but the convex side is simply steeper than the concave side, and that would actually just make it a little steeper on the front, a little flatter on the back. So if this is a +7 and a -5, +7, -5, I'm looking at about a +2. It's still thicker relatively in the middle than the edge. Overall, this would be a plus lens. So now when light comes in here, light comes in and comes to a real focus. Minus lenses, on the other hand, could be biconcave, plano-concave, or again, another meniscus, but this time it's convex on the front still, concave on the back, but the concave is steeper. So if it's a +4, -7, that'd be a -3. So again, all these are minus lenses or diverging lenses. And here, as we have our light parallel entering a lens, it's going to diverge and all the light rays will never meet. But if we were to pretend, draw, measure, extrapolate where these would meet, if I, instead of going in the direction, pretend where they would have been coming from, back here they'll come to a point, that's the focal length of a minus lens. So we can't, there's nothing here to measure, but we can sort of extrapolate out or draw out if we had a little diagram, and we can measure from this lens to this part here, and that's the focal length of a lens. So the formula, for our purpose in low vision, we're going to do a lot of plus lenses. So the focal length is the distance you have to hold the plus lens or magnifying lens to create a clear image. I couldn't take a +20 lens, which has a focal length of 5 centimeters, and hold the image, hold my reading material out here. It'll just look too fuzzy. I have to hold it at the focal point of the lens. So we have to be able to calculate that so we know what we're doing. We have to also be able to convert from meters to centimeters or millimeters on a dime. So remember, in really basic, 1 meter equals 100 centimeters. Centi is 100. And millimeters, 1,000 millimeters. So if somebody says I have a focal length of, say, 50 centimeters, you have to be able to say that is 0.5 meters. If it's 25 centimeters, we have to, and again, 100 and 1 meter, well, if I took 50 centimeters and divided it by 100, that would give me 0.5. 25 divided by 100 gives me 0.25. So if you have the centimeters, simply divide it by 100. That'll give me the number of meters. And again, you can extrapolate this out. We're going to be doing mostly centimeters. What's the following focal length of the following lenses? If I have a +1 diopter, I'm going to have light coming in, and it's going to hit it, and this is a plus lens, so it should converge. If it converges, I should be able to measure this from here, this focal point to here should be 1 meter. 1 over 1 meter, 1 over the focal length gives me 1 diopter. And minus lens, well, remember, if I do it this way, it's going to hit here, and instead it's going to diverge. Well, if I drew back the direction on which these light rays appear as if they're emanating from after they come out of the lens, and measure back, if this is a -1 diopter, I expect this to be -1 meter. +2.5 diopter, if I do here, and again, let me just make sure I have this. Oh, my computer's slow as molasses today. I apologize, guys. There we go. There we go. I missed this slide somehow. I apologize. So the focal length is simply, and this is back basic and review, if I have the focal length, I can find the focal length by simply taking 1 over the value of the lens, so the dioptric value of the lens. If I have a +1, 1 over 1 diopter equals 1 the focal length of 1, and the focal length is in meters for this formula. If I have the dioptric value, if I know I have a plus 1, if I know the focal length is 1 meter, 1 over 1 meter, 1 over 1 gives me a dioptric value of 1. And we can continue to do this formula. So if we keep going to these, so plus 250, so here's the plus 250. If I have light coming in that's parallel, and it's going to converge, I'm going to ask you for the focal length. The focal length is simply 1 over the dioptric value, 1 over 2.5. And if you divide 1 by 2.5, you end up getting a number of 0.40, and that's in meters. So it's less than a meter. And it makes sense. If the plus 1 diverged to 1 meter, a plus 250 is going to converge it more. It's going to have a shorter focal length. It's stronger. It converges more, so the focal length is closer to the lens. 1 over 2.5 is 0.4, so it'd be 0.4 meters or 40 centimeters. And a 5 diopter lens, well, I want to know the focal length. The focal length equals 1 over the dioptric value. So 1 divided by 5. 1 divided by 5 is 1/5, or 0.2. Do it in your calculator if you'd like. So that would give us an answer of 0.2 meters, and we can convert to 20 centimeters. Finally, 10 diopter lens, and notice how I'm trying to make it stronger and stronger. 1 over the focal length of a 10 diopter lens is 10 centimeters, or 0.1 meters. 1 over 10 is 0.1. And let's even do a plus 20. What the hell? Plus 20, 0.05. 1 over 20 is 0.05, or 5 centimeters. And this is going to come in very handy, or very important. So notice how the stronger the lens, the stronger the dioptric value, the more plus lens we have, the more it converges. The more it converges, the more powerful it is, the closer that point comes to where the lens is. And this is going to be very important in low vision, especially with single lens magnifiers like handheld magnifiers. We're going to have to hold the reading material closer and closer and closer the stronger the lens is, and that's why. So this was just our quick review, but I wanted, if I give you a magnifying lens of sort, and I said this is a plus 8 diopter lens, you should be able to tell me that the focal length is 0.125 or 12.5 centimeters. And we're later on going to say that's how close we're going to have to hold that reading material. And so you may find that as someone needs stronger and stronger reading help or magnifiers to get letters big enough so that they can see them, you may find that it's almost counterproductive, because if they have to hold it so close to their face that it's impractical, we may have to go a different route. But you have to understand the basic optics on here. So that was it for our basic math review for focal lengths and plus and minus lenses real quick, mostly plus lenses. And we will post that, and then we'll get to the actual lecture, and we'll see you shortly.